Welcome back. In the last part of this lecture, we'll be looking at derivatives of the other four trig functions and also higher derivatives. To start off with, the reason why we didn't introduce the derivatives of secant, cosecant, tangent, and cotangent is because we want to be able to prove them, and of course we don't want to have to use delta epsilon or limits to make that proof happen. And now that we have the quotient rule and know the derivative of sine and cosine, we can do this. And that's because all four of these functions could be expressed in terms of a quotient involving sine and or cosine. So I'll show you what I mean. And so for all of these little derivatives, again, I can quickly establish them just by using quotient rule. So I'll start with the derivative of secant. If we're looking at the derivative of secant, secant is the same thing as 1 over cosine. And so now I'm going to use my quotient rule, and I have the denominator gets squared. That's cosine squared. The derivative comes up, the denominator comes up rather, cosine times derivative of the top. The derivative of 1 is 0 because that's a constant, minus numerator as it is times the derivative of the denominator, that is negative sine of x. Good. Okay, so now just a little bit of cleaning up and then I'm finished. I can say as far as the numerator goes, you now have positive sine of x. And in the denominator, you have cosine squared of x. And now, how to get the rest of the derivative formula, it's just a little splitting up and we're finished. I can rewrite this as a 1 over cosine times a sine over cosine. And that is exactly secant times tangent. And there we go. That's my proof for the derivative of secant being secant times tangent. The proof for cosecant is pretty much the same thing. So let's do that while we're here. So in this case, cosecant is the reciprocal of sine. So again, quotient rule, we'd have denominator gets squared, so sine squared. Denominator comes up. Derivative of the numerator, that's derivative of 1, which is 0, minus the numerator as it is, times the derivative of the denominator. Derivative of sine is cosine. So we've got negative cosine of x over sine squared. And then, of course, we can split that up kind of in the same way that we did with the secant proof as negative 1 over sine times cosine over sine. And there we go. We've got our negative cosecant cotangent. All right, so let's do the last two. So tangent and cotangent next. So let's look at the derivative of tangent with respect to x. And tangent is sine divided by cosine. And away we go. Denominator gets squared. So cosine squared. Cosine comes up. Derivative of sine is cosine. Minus sine stays as it is, numerator stays as it is, derivative of the denominator is, derivative of cosine is negative sine. And then I'll notice I've got a cosine squared in the numerator, and I'll also have a plus a sine squared, which hopefully that's making you think of your favorite Pythagorean identity that is equal to 1. So we have cosine squared plus sine squared in the top. That's really just 1. So we have 1 over cosine squared and 1 over cosine squared. Cosine is reciprocal of secant, so this is secant squared. Not bad. And we'll do now the same thing. Our proof for cotangent is going to work pretty much the same way. So cotangent is cosine over sine. And quotient rule says we'll have in the denominator sine squared. Then sine will come up. Derivative of cosine is negative sine. You'll have minus. Cosine will stay as it is. Derivative of sine is cosine. We'll have negative sine squared minus sine squared minus cosine squared on the top. And this shouldn't be too surprising. This is just negative 1 times our Pythagorean identity. That's really negative 1 of sine squared plus cosine squared. So really, that's the numerator is just negative 1. The reciprocal of sine is cosecant, so really what we have here is negative cosecant squared. And there we go. We've shown all 4 of these trig proofs. That's one of the nice things about this proof, or these 4 proofs in particular. If you're ever lost and you can't remember what the derivative is of tangent or secant or whichever one of these 4 off of your head, as long as you know quotient rule, you can always figure these ones out for yourself. Okay, so we've got a little problem here where I've got a little function, 3 secant x tangent x, and I want to find the equation of the tangent line to that function at x equals pi over 4. So first thing, I know that if I'm looking for any sort of a line, I need 2 things. Number 1, I need a slope, and number 2, I need a point. And as far as the point goes, we've got part of that already. I know what the x value is for the point. That's pi over 4. So the y value, I can find that pretty easily, just putting in pi over 4 for x into f of x. So I'll have 3 secant pi over 4 tangent pi over 4. Secant of pi over 4 is root 2, and tangent of pi over 4 is 1, so I get 3 root 2. Okay, so I've got my point figured out. That's at least one thing. And now the slope. This is where I remind myself that if I'm looking at the slope of a tangent line, that is the value that you get for the derivative at that x value. So if I'm looking for the slope, that means I need to find what is f prime of x at x being pi over 4. So I need to find my derivative, then put in pi over 4. That will tell me what my slope is. Then once I know what my slope is, I can use my slope and my point to come up with my equation. So I guess let's get started with finding our derivative. And we notice here that it is a product. I can imagine this as 3 secant x times tangent of x. So I do have a product of 2 functions, so I'll need to use product rule, number 1, and I'll also need to remember all my derivative rules for secant and tangent. So let's start off. Product rule says it would be the first thing as it is, so 3 secant times the derivative of the second thing. Derivative of tangent is secant squared. And then plus the second thing as it is, tangent, times the derivative of the first. The derivative of 3 times secant is 3 times secant times tangent. So I'm going to do one little bit of cleaning up here. I can say we have 3 secant cubed, and then plus tangent squared, 3 tangent squared secant. Okay, So we're pretty much ready to go. We just have to now find out what is the value when x is is pi over 4. So f prime of pi over 4, that is 3 times secant cubed of pi over 4 plus 3 tangent squared of pi over 4 times secant of pi over 4. Okay, and we've already evaluated secant and tangent at these values before. I know that secant of pi over 4 is square root of 2. So I would have 3 times square root of 2 cubed plus 3 times tangent of pi over 4 is 1. So 3 times 1 squared times square root of 2. If I were to clean things up a little bit further, just here on the side, I'm going to remark to myself that root of 2 cubed is root of 2 times root of 2 times root of 2. That's 2 root of 2. So actually, I can rewrite this as, instead of 3 times root of 2 cubed, it's really 3 times 2 times root of 2, or 6 root of 2. Okay, and that means that really what I've got is 6 root 2 plus 3 root 2, or 9 root 2, and there we go. That's my slope. So now, for me to find the equation, well, I guess I'll have to finish it off here. For me to find the equation of my tangent line, I guess I'll do that over in this little spot. Remember, to find the equation of a tangent line with our slope and our point, we just use our slope point form and say that for our line, it is y minus the y-coordinate equals our slope times x minus the x-coordinate. And then the only thing really to do is just sort of expand this and move everybody over to one side. So when I do that, I'll have 9 root of 2x minus 9 pi root of 2 over 4 plus 3 root of 2. I mean, it doesn't look spectacularly wonderful as a set of numbers, but I mean, not everything has to look nice. There we go. There's our equation of our tangent line to that function at that point when x is pi over 4. Okay, so here's where things can start to get a little bit fun and maybe a little bit messy. We sometimes have to do more than one derivative rule at a time. So sometimes you might have things involving products as well as quotients. So if we're taking a look, for example, at this, I can see that for the function that I have, f of x, it is a quotient. So if I took the derivative of f of x, I'd have to use quotient rule. And I know that when I use quotient rule, at some point I'll be doing the derivative of the top, but the top happens to be a product. So when I do that, I'll have to use product rule. So I basically have a product rule nestled inside of a quotient rule. So this is where, again, maybe diagramming out how we're going to do our derivative first might be a little bit helpful to us. I know that I'm definitely going to be finding a derivative here because we're doing the same thing again. We're finding the equation of a tangent line. I know that if I want to have it at x equals 0, so I guess maybe before I get into the derivative, I'll figure out what my point is. And this is a pretty fast one because when I put in 0 for x, I get 0 over 1, which is just 0. So it looks like we're going through the origin. So it'll be a relatively nice looking equation of a tangent line. We just need to now find our slope. So here I'm going to diagram things out. I won't do derivatives as I go when I do my quotient rule. I'll just diagram out the quotient rule first, which is for f of x, the derivative is, for f of x, the derivative is the denominator squared in the bottom. Denominator comes up times derivative of the numerator. minus the numerator as it is, times the derivative of the denominator. Okay, so I've got myself started here. I've diagrammed out what I need to do. As far as the two little derivatives that I need to do now, I can see that one of them is easy enough. The derivative of 1 plus x, that's just going to be 1. But when I do the derivative of x squared plus 2x times secant, I'm going to need to use product rule, where I have x squared plus 2x is one of the factors and secant is the other. So now I'm going to take the derivative of that little product using product rule. Okay, so we have first thing as it is, derivative of the second, derivative of secant is secant times tangent, plus the second thing as it is, secant, times derivative of the first. The derivative of x squared is 2x, and the derivative of 2x is 2. There we go. So all of that in those big brackets, that's all the derivative of the x squared plus 2x times secant. And then now I still have that second part of my numerator, the minus x squared plus 2x times secant times 1. So there we go. We've got our derivative, and we could, if we wanted to, go ahead and try to simplify it and make it look a little bit nicer. I don't really see the point in doing that here. That feels like a lot more work than it's worth, because we're going to be evaluating things at 0, and so that'll be pretty easy to do, and that'll probably be a lot faster than the simplifying approach. Other thing just to mention here before I do my simplifying, I'm going to evaluate the polynomial parts. That'll be no problem. Good for me to just remember that secant of 0 is 1 and tangent of 0 is 0 as I'm doing my evaluating. So let's get into it. And let's say what our slope is going to be. We'll have f prime of 0. I'll have 1 plus 0, which is 1. I'll have 0 squared plus 0, which is 0, times secant of 0, which is 1, times tangent of 0, which is 0. Secant of 0 is 1. 2 times 0 plus 2 is 2. And then minus 0 squared plus 0 is 0. Secant of 0 is 1. And in my denominator, 1 plus 0 squared. Okay, so actually that's pretty fast and easy to do because almost everything's are zeros here. In my numerator, that's equal to 0, that's equal to 2, that's equal to 0. So if I were to clean things up, I would say that I have f prime of 0 is 2 minus 0, which is 2. Over 1 squared, which is 1. So my slope is 2 over 1, or 2. Okay, so my point is 0, 0. My slope is 2. I guess I'm ready to come up with my equation of my tangent line. So slope is 2. The point is 0, 0. And so we have y minus the y coordinate equals slope times x minus the x coordinate, or in other words, y equals 2x. Okay, I've got a problem here, and this is sort of a good lesson in why we should do some simplifying if possible before we do our derivative. So if I'm taking a look at this, this is really kind of a mess in many ways. It's the same sort of thing as the last problem where I've got a quotient, but inside of my quotient I also happen to have a product. So we'll have that whole product stuffed inside of a quotient rule. So if I just took the derivative as it is, I'd have bottom gets squared, bottom comes up, derivative of the top minus the top as it is, times derivative of the bottom. And derivative of secant, I can do this one right away, that's secant times tangent. I'll have to make that a little bit smaller, I guess. Okay, as far as the derivative of the top part, that's a product, and so for that I'm going to need to use product rule. So filling in that part, the derivative of the numerator, I have first thing as it is, derivative of the second, which is negative cosecant cotangent, and then plus the second thing as it is, times the second, times the derivative of the first, the derivative of tangent being secant squared. Okay, so there's a lot of things that are terrible about this. There is one thing that's kind of nice that I can do to make my life a little bit easier, and that's the following. I notice that I have secant is a factor of the first term, secant is also a factor of the second term, secant is also a factor of the denominator, so I can make my derivative a little bit nicer by canceling the secants from the top with one of the secants from the bottom, so that at least makes my life marginally better. So I've got now negative cosecant cotangent times tangent plus cosecant x plus 1 times secant squared minus cosecant x plus 1 times tangent squared. And this will all be over a single secant. So now simplifying this is not super easy. It's going to take a little bit of work on our part. So one thing I'm going to notice here, and this is, again, the simplifying is maybe made easier the more trig identities you know. One thing I recognize is cotangent and tangent are reciprocals. When you take tangent and multiply it by cotangent, that's equal to just 1. And that's, again, because they are reciprocals of each other. Tangent is 1 over cotangent, and vice versa. So that's one thing I can do to make my life a little bit easier. I have negative cosecant times 1. I notice here that I have for the last two terms, they both have a cosecant of x plus 1 involved. So rather than expanding, I feel like I'll just, from the last two terms, factor out a cosecant of x plus 1. And that'll leave a secant squared minus a tangent squared. Okay, so let's see, where else do we go from here? You might be looking at that secant squared minus tangent squared and having some Pythagorean identity thoughts. And so let's have a little moment upstairs and remind ourselves the identity you're probably remembering is tangent squared plus 1 is equal to secant squared. But of course, if you were to rewrite that, moving the tangent squared to the other side, you would have that secant squared minus tangent squared is equal to 1. So actually we can do a little bit more simplifying by replacing the secant squared minus tangent squared with 1. So what do we have now? We've got negative cosecant plus cosecant plus 1 times 1. Okay, so we're almost there. I feel like I've got only a little bit more simplification to do. And that's this. I see in the numerator, if I were to clean that up, you'd have a minus cosecant, a plus cosecant. That would cancel each other out, leaving just 1 in the numerator. So I would have just 1 in the numerator, secant in the denominator, and then I could say for myself, well, hold on, 1 over secant, that's the same thing as cosine. So my derivative, as terrible as it was, it simplified down to just give me cosine of x. So now I'm going to start off again, and this time, before I take my derivative, I'm going to do a little bit of simplification, and then we'll see how it makes my life a little bit easier. So here, what I'm going to notice is I've got tangent times cosecant plus 1 over secant. And I'm going to do one thing first. I'm going to make this not be a quotient anymore, and I'm going to do that by noticing secant and cosecant are reciprocals. So a secant in the denominator is the same thing as a cosine in the numerator. And then I'm going to also notice for myself that tangent is the same thing as sine divided by cosine. So when I take cosine times tangent, the cosine and the cosine will cancel, leaving just sine behind. So actually I can do a little bit more simplification here and say that we've got sine times cosecant plus 1. And if I just expand that, I'll have sine times cosecant plus sine times 1, which is just sine. And here I'm almost finished. I also know sine and cosecant, they're reciprocals, so if you multiply them together, they're equal to 1. So as it turns out, my original function, which had a quotient and a product buried inside of it, turns out to, when you simplify it, it's just really the function 1 plus sine of x. And so if I were to take the derivative now, it's a lot easier. Derivative of 1 is 1, derivative of sine is cosine, so therefore my derivative is cosine of x. You'll notice that spending a little bit of time up front simplifying saved me a lot of time later on not having to do simplification with my derivative. So I think that's a good thing to sort of keep in mind. Whenever we've got a function, ask yourself if it could be made simpler, and if it can, probably a good idea to do so. And that actually kind of takes us into a nice place here, because that is sort of a running theme with higher order derivatives. So if we're interested in the second derivative or the third derivative or a higher order derivative, what we're talking about is taking derivatives of derivatives. So if we have a function f of x and we take its derivative, we call that the first derivative. And that's f prime of x. It's measuring how is f changing. If we took f prime and took its derivative, that would tell us how f prime is changing. That would be the second derivative, and we would write that with f with 2 little tick marks. And we could continue going if we wanted to know how the second derivative was changing. We could take the derivative again and get the third derivative, and keep going and keep going. Same as before, unfortunately, we've got multiple notations for derivatives. So we introduced this at the very beginning of Chapter 2, the various notations for the first derivative, but similarly, the second derivative could be expressed in the same bunch of different ways as can the third derivative or fourth or fifth or any other higher order derivative. As a running theme, I said as far as simplification goes, generally you'll want to do some simplification after you find a derivative before you go on to find that higher order derivative. So if I was finding the second derivative, I'll find the first derivative, simplify it, then find the second derivative. Okay, so let's take a look at this problem. I have a function, not terribly bad. It's got 2 factors, an x and a cosecant of x. I'm looking for the second derivative, though. So for the first derivative, it's a pretty straightforward product rule. First thing as it is, derivative of the second, derivative of cosecant is negative cosecant cotangent. plus the second thing as it is times the derivative of the first, and the derivative of x is 1. I'm just going to clean things up a little bit here. So I've got negative x cosecant cotangent plus cosecant. I'm looking at this and I'm thinking about taking my second derivative, and right now I've got, as far as second derivatives go, a problem at least that I don't like too much, which is the first term is a product of three factors, a minus x, a cosecant, and a cotangent. So if I were thinking about this as a product rule, I would have to do kind of a product rule within a product rule. I don't really like that all that much. My product rule that I'm comfortable with is for two factors, so I'm going to make a little switch here. I'm going to notice that cosecant could be factored out of both terms. This is what I meant about maybe doing some simplifying first before you go ahead and start taking second derivative. If I'm looking at what I have now, this is a little bit more straightforward for me mentally, at least. I won't have to deal with a product of three factors. I will have a product rule. I have cosecant as one factor and then all of the rest as a second factor. And when I do the derivative of that second factor, there will be a product rule within it. But I think that's a little bit more straightforward. A product rule of two factors within a product rule of two factors. I'm more comfortable with that. When I do my second derivative, I am going to diagram things out, and then we'll do the actual taking derivatives afterwards. So by that I mean I see that I have a product of two factors, so my derivative will be first thing as it is times derivative of the second plus the second thing as it is times derivative of the first. Okay, so now I'm ready to go and do my derivatives. So let's start with the first part here. As I said, I note that I've got another product rule going along here. I've got this minus x times cotangent of x. So I guess let's do what we need to do and take our derivative with product rule. First thing as it is, negative x times the derivative of cotangent, which is negative cosecant squared, plus the second thing as it is, cotangent, times the derivative of the first thing. The derivative of negative x is negative 1. And then plus 1, derivative of that is 0. And I don't think I'll be able to fit it all on one line, so I'll sort of have to straddle two lines here. For the second term, I have the negative x cotangent x plus 1 times the derivative of cosecant, and the derivative of cosecant is negative cosecant cotangent. Okay, so a little bit of cleaning up that I'll need to do here. So I've got cosecant of x times, I have positive cosecant squared times x minus a cotangent. And then I have plus x cosecant cotangent squared, and then a minus cosecant cotangent. Okay, let's see if there's anything else that I can do to clean things up here. I'm going to expand that first bracket, and then maybe there might be a little bit of nice things that happen. Maybe, maybe not. We'll find out. Let's see. I can say that actually I'm not going to do that. My original plan was to multiply cosecant into the second bracket, then see what happens. But I'm actually noticing that I have cosecant as a factor in the first term. Cosecant is also a factor in the second term. Cosecant is also a factor in the third term. So it actually makes more sense to just factor cosecant out. And what am I left with? I have a x squared cosecant x minus cotangent of x. From the second term, I'll have an x cotangent squared. And from the last term, I'll have a minus cotangent. So I guess that answers my question as to is there anything I'll be able to do? And the answer is one little thing, which is I can combine the two minus cotangent x's. So I've got an, oh, I just noticed I got a little sloppy with my writing and this square migrated. Shame on me. Minus x times cosecant squared. It was the cosecant that was squared, not the x. Good thing I noticed that. Okay. And there we go, we have our second derivative. One thing that you'll probably notice as you do some practice problems on higher order derivatives is that even for a relatively simple looking function like x cosecant x, the first derivative got a little bit nasty, the second derivative is even messier, and in fact, the third and fourth and higher order derivatives get messier and messier and messier, and that's sort of a trend that you'll notice, that higher order derivatives can often be a little bit more complicated.